without a tail, shining directly toward the sun, and on a path that cannot be random. The latest image from the European Space Agency reveals something that no comet observer expected. Instead of the promised steam trail, a solid core brightly glows, defying cosmic laws, moving past Mars towards Jupiter. If this is just a comet, it rewrites the rules of what comets are capable of. But if this is not the case, the stakes rise sharply. The guest behaves not like a wandering stone, but more like a relic or probe. And what will happen next if the explanation fails? October 25th, 2020. The ExoMars Trace Gas Orbiter targets its camera at a faint visitor passing through the Martian sky. For several nights, the instrument team gathers a sequence of 5-second exposures, unusually long for a spacecraft designed to capture the rusty red surface of Mars, not the blackness beyond. Each unprocessed frame captures a tiny blur against the backdrop of pinpoint stars. The comet's core, though unresolved, is clearly wider than any star in the field. This difference, twice the width of the star's scattering function, indicates the presence of a compact coma, even if the core itself remains hidden. To understand such weak signals, the team resorts to image overlaying. Dozens of frames, each cleaned of cosmic rays and background noise, are aligned according to the presumed movement. Median overlay suppresses artifacts, while calibration files, offsets, dark and flat frames correct the device's operational features. As a result, a clear composite is produced, where the comet's core stands out, surrounded by a faint halo, but without signs of a classic tail. Photometric analysis confirms that the observed width is not just an optical trick or motion blur. The stars remain sharp points. Only the comet shows this subtle diffusion. Each step is verified. Astrometric reference stars capture the field. Logs of exposures and data on the spacecraft's position are compared to the predicted path. The team compares the data with known image artifacts, searching for characteristic lines or traces of cosmic rays. Nothing of this sort is found in the final product. The image of the comet is stable and real. However, despite all efforts, the core cannot be separated from the surrounding haze. The camera's resolution limit at 30 million kilometers means the core remains a mystery, characterized only as unresolved but extended. Raw and calibrated footage, while necessary for judicial review, is not always published immediately with the first data. Access to the complete set sometimes requires formal requests and sometimes even appeals under the Freedom of Information Act, while the world sees a clear, bright core with a dim solar glow. There is no classic comet tail. Other Martian instruments, like Mars Express, struggle to record anything. Their short exposures in various cameras barely register a signal. There is no direct detection, only hints in the noise. The European Space Agency's policy is aimed at quickly providing the public access to data, but processed datasets and calibration products often remain closed until analyses are completed. The scientific community eagerly awaits the raw footage and full transparency. Without them, the boundary between signal and artifact remains a matter of trust and protocol. Ultimately, we have a dataset that requires caution. The core is clear, the coma is real, and the absence of a tail is not an illusion. However, the final answers about the size, structure, and true nature still depend on data locked behind administrative doors, awaiting the next round of verification. Comets, by their nature, are subject to sunlight. As they approach the inner part of the solar system, ice that has been trapped for millennia begins to evaporate. This process, called degassing, creates jets of gas and dust ejected into space. But the direction of these jets is not random. The sun, emitting a constant stream of photons and charged particles, acts like an unrelenting wind. The pressure of radiation, the physical impact of sunlight, and the solar wind, a flow of charged particles, push material away from the sun. As a result, we have a law. The tails of comets always point away from our star, regardless of the direction in which the comet itself is moving. Imagine a garden hose spraying water. If you aim the nozzle at a fan, the stream of water will be deflected by the wind. The tails of comets behave similarly. The dust tail, made up of small particles, reacts most strongly to solar light pressure, spreading into a broad, bright arc. The gas tail, shaped by the magnetic field of the solar wind, often forms a sharper, blue-red stream. Both tails are on the side opposite the sun, as physics operates there. This is not just a theory. Every comet documented over the centuries, from the famous return of Halley's comet to the recent interstellar visitor, I or Boris, has followed this rule. Even when the comet orbits the sun and changes direction, its tail flips, always remaining pointed away from the sunlight, and its orientation acts like a compass, indicating to astronomers where the sun is, even if it is out of frame. The details can be subtle. Flashes, rotations, and jets from specific openings on the surface can create breaks or knots in the tail, but the dominant force remains the same. Sunlight and solar wind determine the direction of the flow. When the activity of a comet increases, its tail becomes longer and brighter, always pointing away from the sun. If the tail points anywhere else, especially towards the sun, it violates the most fundamental expectations in comet science. That is why astronomers closely monitor the direction and shape of a comet's tail. It is not just a beautiful element, it is direct evidence of active physical processes. The anti-solar tail is so fundamental that any deviation immediately causes astonishment. When an object like the triple comet Atlas disrupts this rule, it is not a minor anomaly. It is a challenge to the entire system that defines what a comet is and how it behaves under the influence of the sun. A body called Tri-I Atlas races through the solar system at nearly 130,000 miles per hour, taking it far beyond the sun's gravitational influence. However, its trajectory has forced orbital dynamics experts to rethink their models. Instead of barreling into the system at a sharp angle like most interstellar objects, Tri-I Atlas approaches almost exactly along the plane of the ecliptic, the very plane on which the major planets orbit. This is not just a geometric curiosity. The probability that an object from deep space can enter the solar system's disk rather than slipping above or below is extremely low. Some experts estimate the chances at less than 1%, although no peer-reviewed simulation has yet been able to accurately determine the true frequency of such events. The intrigue intensifies with a sequence of planetary encounters. After entering the ecliptic, Tri-I Atlas passes near Mars. A few weeks later, it approaches Jupiter. Two gravitational giants are in almost perfect alignment for what spacecraft engineers call a gravitational maneuver. This maneuverability, familiar from decades of planetary research, allows for borrowing a bit of momentum from a planet, altering its trajectory and increasing speed. For a comet, such a coordinated sequence of encounters is rare. For an interstellar object, it is almost unprecedented. The dynamics teams began conducting Monte Carlo simulations to check if this choreography could be a cosmic random coincidence. One thing is clear so far. It is a rarity. Random interstellar objects, modeled as incoming from all directions, should only occasionally align along the ecliptic, and even fewer should pass between two large planets in quick succession. The previous interstellar visitors, such as Oumuamua in 2017 and Boris in 2019, followed more typical steep trajectories, never approaching planetary maneuvers. The trajectory of Tri-I Atlas stands out significantly. Some consider it a statistical coincidence, an event 1 in 10,000 that becomes inevitable when billions of objects intersect over billions of years. Others see it as some kind of design, if not intentional, then at least due to some unknown dynamic process. The lack of published probability keeps the discussion open, but the sequence of movements, entering the ecliptic, passing by Mars, approaching Jupiter, looks more like a mission plan than the path of a wandering snowball. So far, data is lacking, but questions are multiplying. Thermal models awaited a fragile traveler, worn by centuries in deep cosmic space. Instead, data from Hubble, the James Webb Telescope, and images from Mars' orbit indicate a core that is at least 3 miles wide, possibly more. This is not just a lot for an interstellar object. It is a giant by comet standards, rivaling the largest comets ever measured in the solar system. Survival on such a scale requires not only luck. Most smaller bodies would have been destroyed by cosmic rays and micrometeoroids long before reaching our area. However, here lies Tri-I Atlas, whole and intact, its core hidden beneath a dense, blurred fog. Spectroscopists studying the dim light discovered something even stranger. The optical spectra obtained from Keck and VLT data show strong emission lines of nickel, pure, clear, and indisputable. But iron, a common companion in comet chemistry, is absent. Not just in small amounts, but completely. The detection limit of iron is 10 times lower than the signal of nickel. However, no traces are observed. In the comets of the solar system, iron surpasses nickel by orders of magnitude. Here, the ratio is turned upside down. Some speculate that nickel is connected in metal organic complexes, or that iron is trapped in dust grains that are too large to evaporate. Others wonder if this substance was formed in an environment different from the known cometary cradle. The molecular story adds another layer. Spectra in the near-infrared range from JWST show both water and carbon dioxide, but in a ratio that breaks the rules. The ratio of carbon dioxide to water is 0.57, nearly twice the average for the solar system. Most comets lose water as they approach the sun, while carbon dioxide lags far behind. Here, carbon dioxide is almost on par with water, suggesting either a different mixture of ice or a formation history in a colder region rich in volatile substances. Some laboratory analogs hint at similar chemistry in carbonates, but nothing matches the complete set of characteristics. Polarimetry, the fine science of measuring the orientation of light, presents yet another anomaly. The negative minimum polarization of the comet, measured at -2.7%, is deeper than that of typical comets with a low inversion angle. Only highly porous grains of magnesium silicate, mixed with ice, correspond to the models. This dust is darker, fluffier, and more complex than in textbooks about comet tails. Each discovery strengthens the feeling that the three IATLs are not just a statistical anomaly, but a physical one. Large, complex, and chemically inappropriate. Evidence, step by step, refuses to fit into any familiar patterns. The high-definition camera, HiRISE on board NASA's Martian Reconnaissance Orbiter, was scheduled to observe the I-Atlas during its closest approach to Mars. The observation window was narrow, just a few days in early October 2025. However, the operation took place against the backdrop of the closure of the U.S. government. Data processing and public release were halted. Images, if obtained, were stuck in a queue, blocked by administrative barriers. The mission operations leader described the situation as disappointing, but not unprecedented, pointing to strict protocols governing planetary data, especially as mission funding runs out. In this vacuum, rumors surged. Forums and social media buzzed with speculation. Did HiRISE see something so unusual that it required approval from higher authorities, or was the delay just another victim of bureaucracy? Unverified claims spread. Some suggested an internal discussion about what the images depicted. Others proposed theories of technical failures or even deliberate suppression of information. The lack of official updates only fueled interest. Viral publications recycle old images, overlaying them with speculative elements, creating a closed loop of anticipation and suspicion. Meanwhile, scientific groups waited. A high-rise complex designed for mapping the surface is testing its limits while targeting weak, fast-moving objects like 321 Atlas. Each frame requires careful calibration, dimmed shots, flat fields, and precise timing. Without access to raw data and complete calibration products, external experts could only guess what the camera might have captured. Calls for transparency grew louder, echoing in both professional circles and the wider public. The lesson was clear. When data is concealed, even for procedural reasons, the narrative slips out of the control of those closest to the facts. Scientists have many theories, but the weight of evidence must be measured, not just imagined. Avi Loeb, an astrophysicist from Harvard known for challenging established views, suggested that when several independent anomalies converge, such as strange chemistry, the coma of the sun tree, and a trajectory resembling a flight plan, the likelihood of unnatural origins increases above background noise. He publicly spoke of the probability of artificial origin being 30 to 40%, not as a calculation, but as a heuristic to keep the door open. The scientific community, in turn, insists that such figures remain personal estimates unless based on formal analysis. Neither any peer-reviewed article nor official report assigns a probability figure that Trio 1, Atlas, is an engineering object. More important than any single statement is the current state of affairs. Each hypothesis, a standard comet, an ancient probe, a technological relic, an automatic scout, makes verifiable predictions. The null model expects a classic comet, a random orbit, an anti-solar tail, familiar ratios of volatiles, iron overshadowing nickel. A probe or relic must demonstrate a deliberate trajectory, not erratic chemistry or metallic signatures that do not correspond to natural formation. A sensor or time capsule may transmit irregular signals or display engineered isotopic ratios. These are not just labels, but working hypotheses, each of which has potential refutations. If iron is found in the coma during the next round of spectra, or if high-quality images reveal a cracked, icy surface, the arguments for the extraordinary will collapse. If anomalies multiply, if the trajectory is confirmed through gravitational maneuver simulation, if the nickel theory ratio remains inverted, and if polarization signals are stable against comet models, then the probability must be updated. Both Lobb and his critics agree that extraordinary claims require extraordinary evidence, and each new data point either strengthens or weakens the case. The task is to maintain the integrity of the network, allowing evidence rather than headlines to determine what story 321 on Atlas is really telling. Protocols for dealing with interstellar visitors have never been more relevant. In Vienna, the United Nations Committee on the Peaceful Uses of Outer Space discusses the framework for rapid response that will enable coordinated monitoring and risk assessment immediately after the confirmation of a new object. The proposal calls for automatic data exchange, expedited access to telescopes, and the establishment of a permanent group to address biosecurity and planetary protection issues. Although no agreements currently exist, the pressure to take action is increasing. The scientific list of necessary actions is clear. High-quality images, preferably from both the Earth and orbit, can ultimately clarify the structure of the core by revealing its surface features or possible artificial constructions. Metallic spectroscopy, especially in the ultraviolet and near-infrared ranges, will determine the ratio of nickel to iron and reveal signs beyond natural chemistry. Extended polarimetry at various phase angles can refine models of the structure and composition of dust grains. A thermal map using infrared sensors in space can reveal thermal patterns indicating whether the core is solid, cracked, or layered with exotic materials. Precise astrometry tracking every minor shift in an object's path can reveal non-gravitational forces or even controlled motion. Each of these research directions has a dual purpose: to confirm the null hypothesis of a natural comet and to search for signs of something artificial. The international community faces a choice: wait for anomalies to accumulate or develop a protocol to prioritize the facts. The next interstellar visitor may arrive without warning. At this moment, the call is simple: demand open data, support global coordination, and follow the facts wherever they lead. However, important high-quality images from Mars orbit have still not been published, and the true source of several anomalies remains unverified. Calls for the creation of transparent and swift international protocols are now echoing throughout the scientific community as facts require further analysis. Currently, records show that 3 atlases do not fit into known natural categories, leaving their origin an open question and their study a priority for future missions.